So we'll take up this small little segment in solid state. You'll want to give a heading like defects or imperfections in solid. And right away, when it comes to the defects and imperfections in solids, uh, before we go into any of the imperfections, hey, let's know that no solid or crystal is 100% perfect. No solid or crystal is 100% perfect. It's perfect only at 0 Kelvin minus 273 degrees Celsius. So which will mean there's going to be some defect or imperfection in all crystalline solids. And these defects are generally called thermodynamic defects. You know, they're called thermodynamic defects. They're called thermodynamic defects because, you know, you'll see they'll depend or they'll increase with temperature. So because they're going to increase with temperature, at minimum possible temperature, I told you at 0 Kelvin, which is hypothetical, there's going to be no imperfection. I'm going to call them thermodynamic defects. I'll give you some key points and you'll want to copy it right away. I'll want to confirm once that my voice is loud and clear. The most common type of defects we'll come across are going to be point defects. Please respond if you're able to hear me loud and clear.
Yes.
So lattice points, you know, the atoms and their relative positions are called lattice points. So points or atomic imperfections are broadly going to be of three types, you know. Two prominent, they're called stoichiometric and non-stoichiometric defects. There's going to be another type which is because of an impurity creeping in, but these are the two prominent ones. I repeat, there could be a third type of defect due to impurity, but we'll take, you know, only these two into account. Stoichiometric defects, again, the two prominent ones are the very popular Schottky and Frenkel defect. I hope you're noting it down. At any point of time, if there is a problem, you'll want to let me know. The most common type of defects are point defects. Stoichiometric defects are those where despite the defect or imperfection, the stoichiometry of the molecule is not disturbed. So if I begin with stoichiometric defects, these defects are such that the stoichiometry isn't disturbed where in the two common types. Now stoichiometry isn't disturbed means the ratio of cation versus anion is intact. So basically the stoichiometry of the formulae remains the same. And as I told you, the two prominents being Schottky and Frenkel. Schottky defect is the one where you'll have equal number of cations and anions missing. You just want to copy these key points. Equal number of cations and anions missing from the lattice points. I hope you're noting it down. And because equal number of cations and anions are missing, there will be no net change in the formula or stoichiometry of the compound. I repeat, stoichiometric defects do not disturb the ratio of cation and anion, and equal number of cations and anions go missing from the lattice point. Both stoichiometry and electrical neutrality is maintained. I hope you are noting it down. And it's going to be there in, ionic solids. It's going to be there in ionic solids which have high coordination number. So note down these 2 points. They're found in ionic solids having high coordination number, and B, cations and anions of similar sizes. I hope I'm giving you enough time to note down things. You can take down examples. The most common are group 1 halides, sodium, potassium, cesium, chlorides, bromides. I repeat, I hope you're noting it down. And now in a regular geometry of cations and anions, if you have A plus and then B minus, and you have A plus and you have B minus, as some symmetrical arrangement of cations and anions, this is how I symbolically represent a Schottky defect, where I'll claim equal number of particles are missing. So if equal number of particles are missing, in this particular arrangement, obviously it's three-dimensional across the length, breadth, and height. If equal number of particles are missing, allow me to do the following. I'll believe that, say if this B is missing, so is an A here. So if this is a vacant site, this is another vacant site. Number of cations and anions missing are equal. Schottky. One way I kind of try to remember it differently from Frenkel. Schott means something which is gone. So it's gone, missing. Schottky. Whereas in Frenkel defect, you won't have particles missing. In Frenkel defect, you'll have particles going into an interstitial position, which is generally a cation being smaller. So in Frenkel defect, right away, ion is missing from lattice point and goes into some interstitial position. Now, this is more likely to be a cation, which is generally smaller. Yet again, because there is no net loss, you can claim that both stoichiometry and electrical neutrality is maintained. So it's a kind of stoichiometric defect again. But again, if I have to, compare it with a Schottky defect, and this time, this A plus B minus, A plus B minus, A plus B minus, A plus B minus, I repeat, generally the cation is smaller. Generally the cation is smaller. So you'll have a cation missing. Suppose this cation is missing. So this is a vacant site, this is a vacant site. But this cation, would be somewhere here. This would be somewhere here. Interstitial position is obviously this position between the layers. And right away, one difference between Schottky and Frankel you can figure out is, in Schottky, because the number of particles are actually lessened, the density is lowered. The overall density of the crystal is lowered. Whereas in Frankel, the density is the same because they're not gone. And A plus missing here would go into an interstitial position. And this is one basic difference between Schottky and Frankel defect. Naturally, with any kind of defect, two things will certainly happen. So the effect of any defect would be A, dielectric constant will increase. You just want to take down these key points. And the stability decreases. So this is common in any kind of defect. The stability will decrease, dielectric constant will increase. Now, when increase in dielectric constant will certainly bring a decrease in conductivity. But as you could understand, the basic difference between Schottky and Frankel is, in Schottky, because the number of particles is lessened, they're missing. The density is lower, but in Frankel, the density is same because the cation would go into the interstitial position. I hope you are understanding me. One way to avoid a confusion between Schottky and Frankel is, as I told you, in Schottky, one way of remembering is Schott means it's gone completely. It's out of the crystal, whereas it's out of its lattice position only and would be there in an interstitial position. If you're happy with this, we'll want to move on. An increase in dielectric constant will mean decrease in conductivity. And the stability decreases because obviously the lattice energy decreases. The lattice energy decreases. Any kind of imperfection or defect, lattice increases, decreases, and the stability decreases. If you're happy with this, you'll want to respond, and I'll want to move on to the non-stoichiometric defect. बच्चे लोग हाँ ना बोलो. Before we make headway, an important information could be I mean, like I told you, in Schottky, it's about particles having high coordination number and cations and anions of similar sizes. Frenkel, and you'd see here it would happen in ionic solids, where, and again, this is easy to relate to. Yeah, because you have to allow the particles, to move out of their own positions to an interstitial position. It's possible only if there is no coordination number. Obviously, if there is no coordination number, they're kind of less surrounded and easy to come out of their positions. And this is when cation and anion have dissimilar sizes. Again, this is not hard to understand because only if the sizes are dissimilar, anion could kind of hide in the layers. So generally here anion is far less smaller than the cation. So there's again one basic understanding, one basic point you'll want to remember. In Schottky, the coordination number was high and the sizes were similar, whereas in Frenkel, the coordination number is low and the cations and anions have dissimilar sizes. One important information I wanted to give you, and you'll want to note it down, is AgBr has both Schottky and Frenkel defects. Now, so far we have been talking about stoichiometric defects, which I repeat are the ones where the stoichiometry remains the same. Equal number of ions are missing in Schottky. Frenkel में naturally the cation goes into the interstellar space and leaves its own position. Frenkel का भी example लिख सकते हो, zinc sulfide AgCl AgI. Frenkel का भी example लिख सकते हो, zinc sulfide AgCl AgI, and AgBr will have both. So these are the most common examples which have come and are likely to come on any of these exams. Rest I hope is being understood. I hope you're noting it down. Please let me know if there is a problem. And now we'll want to move to the non-stoichiometric defects. Somebody will want to respond to say yes or no and we'll move on.
Yes.
Can I move to the next frame?
Yes.
Because it is hardly a few set of information. I did not want to have pictures and diagrams and unnecessarily complicated. So now I'm talking about non-stoichiometric defects. Now when it's non-stoichiometric defects, naturally the ratio of cation versus anion is disturbed, is not going to be the same. And they're basically either going to be a case where you have a metal excess or a metal deficiency. Metal is certainly the cationic part of the salt. Metal excess is again either due to anionic vacancies or due to extra metal ions. Now, anionic vacancies will be when the anions are missing, anions are missing, and those spots, they're called holes. The spots where anions are missing, those holes are filled by electrons. This is called electronic neutrality. If you have anions missing, now this is again because of anionic vacancies, anions are missing and the corresponding holes are filled by electrons. This is certainly going to be more common in, this is more common in cases where Schottky defect is likely. So this is like Schottky defect. Again, alkali halides are the cases with Schottky defect. So alkali halides, if heated in an atmosphere of alkali metals, and the holes in which the electrons are called, they're very popularly called as the F centers. The holes where the electrons are filled, they're called the F centers. This is a German word, Farben. This can bring color. This can bring color into the compound. This can bring color into the compound. Metal excess defect is naturally due to some metals, extra metals occupying interstitial spaces. So this is more like a Frankel defect, and a very common example is zinc oxide. So the yellow color of zinc oxide is because of extra metal ions. When zinc oxide is heated, it loses oxygen. The extra metal is accommodated in interstitial sites. The yellow color and the electrical conductivity of ZNO is due to extra metal ions. So unnecessarily, I'm not going to give you any diagrammatic view of this, because it is eventually going to look like the following. It's eventually going to look like the same A plus B minus 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 kind of an arrangement. Where in this case B minus are missing, which is more like I'll kind of have a vacancy here, and this is going to be filled by an electron for electrical neutrality. This is called a hole or an F center. It's more like the Schottky defect, and alkyl halides when heated in alkali vapors at times, have color because of this kind of anionic vacancies. So anan is missing, and it's not a stoichiometric defect because only anan is missing. Remember, in Schottky, equal number of anion and cation were missing, so it was a stoichiometric defect. Here, the stoichiometry is going to get disturbed. Similarly, when it comes to extra metal, in extra metal, I could again go like A plus B minus A plus B minus A plus B minus, and I'm deliberately not filling it up, and you'll have some A plus extra here. Now this A plus extra would again be neutralized by some negative extra electron trapped here, and the classical example of zinc oxide is yellow when hot, is about extra zinc ions in the interstitial spaces. This far and no further, you just have to know this example. Now, whether it's anionic vacancy or extra metal, you'll have an excess of metal. Alkali halides having Schottky defect, and alkali halides if heated in vapors of alkali vapors, heated in alkali vapors can have color because of metal excess defect due to anionic vacancies. Zinc oxide, in both cases you have extra metal. In metal deficiency, have you copied it down? Have you copied it down? Because we are going to be in the last lap now. Another 5 minutes and we'll be done with this. Now, metal deficiency again could be because of two reasons. Like extra metal could be about anion missing or extra cation interstitial species. Metal deficiency could be due to one, cation vacancy. So if you have A plus B minus 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 a plus. Equal number of particles are not missing. Had it been equal number of particles missing, stoichiometric will not be disturbed and it will be Schottky defect. Equal number of particles are not missing. What's missing is a cation. You know, when a cation is missing, suppose this cation is missing. This is metal deficiency due to a cation vacancy. It's metal deficiency due to a cation vacancy. Yes or no? And to maintain electrical neutrality for this vacancy, you had an A plus here. To maintain electronic neutrality, what will happen is this A plus will become A plus 2. This A plus will become A plus 2. Now, to maintain electrical neutrality, this A plus will become A plus 2. So naturally, this can happen only in cases where you have variable valency. So this will happen only in cases with variable valency like transition metal oxides. So ferrous oxide, nickel oxide, ferrous sulfide, variable valency, and transition metals only, and FeO and FeS and NiO are the examples which you can relate to here. The other possibility of metal deficiency could be certainly because of extra anions in interstitial species, and because anions are generally larger, this is only for a possibility. You know, no such case is known. And you know, this is exactly how much you're supposed to know to solve questions which will come in the real exam. These are the non-stoichiometric defects, where the number of cations and anions will be different. So I started with metal excess, which could be because of more anions missing, but only anions missing, not the cations. So those anions missing will create holes which will be taken up by electrons, which are called F centers, German word Farben. You have color, alkali halides if treated in vapors of alkali can give you colored stuff. That is because of, you know, a defect. And metal excess could be because of anion missing, and missing is like Schottky defect, or extra metal in interstitial species, which is like Frenkel defect. But they're not Frenkel and Schottky defects because the number of particles aren't equal and they are non-stoichiometric in nature. Metal deficiency similarly could be either because of cation vacancy, which I told you would be electrically maintained by another cation going to a higher oxidation state, and now variable oxidation state, variable valency is certainly a property of transition metals only. So, you know, the examples are ferrous oxide, ferrous sulfide, NiO and all. So, you know, I think this much would take care of the questions which can come in exams other than JEE mains. So, as far as I remember, even in WBJEE, you have solid state. In different exams, you have solid state, and I just had to cover this portion of crystal defects. You know, it would have taken hardly half an hour and 2 to 3 pages in your notebook. But if you remember these key points, like, are you done with this? Is everyone done with this?
Yes, sir.
I go back to the previous page. Stoichiometric, Schottky, equal number of ions are missing. मतलब यहाँ से B माइनस गया तो यहाँ से A प्लस गया. ये आयंस मिसिंग होता है अगर कोऑर्डिनेशन नंबर ज्यादा होता है और साइजेस सिमिलर होते हैं. ये फ्रेंकल में ऐसे याद रखना आसान है कि अगर कोऑर्डिनेशन नंबर कम रहेगा तभी इट कैन स्लिप इनटू अ गैप, and obviously if the sizes are dissimilar then a small one can hide here. So the reverse of this will be for Schottky. It's absolutely missing. Shot मतलब बंदूक से जैसे गोली मारा गायब हो गया. Density इसमें कम होगा, इसमें density कम नहीं होगा. यहाँ पे it has to slip into a position, so naturally you'll want coordination number to be less and the sizes to be dissimilar. You know, these are tricks in which I want to remember it. The differences density is going to be lowered in Schottky and not in Frenkel. Schottky is going to be common in alkali halides, and I've given you potassium chloride, bromide, lithium chloride, sodium chloride as the example. Frenkel is going to be, common in zinc sulfide, silver chloride, AgI, AgBr में दोनों common होता है. A common effect is any kind of imperfection, will decrease conductivity, increase dielectric constant, will cause lattice energy to be lowered and stability to be decreased. But here, because the number of ratio of cation ions are equal, we call it stoichiometric. Non-stoichiometric is when either you have more of metal, and again, no, this is not rocket science. You'll have metal more if anions are missing, which is like Schottky defect, or if metals are, sneaking into the interstitial spaces, which is like a Frenkel defect. वहाँ पे zinc oxide याद रखो, यहाँ पे alkali halide color याद रखो. Metal deficiency will be when cation is missing, and if a cation is missing, it will be compensated by another cation going to a higher oxidation state. So naturally, it's going to be more likely in cases where variable oxidation state and variable valence is possible. I'll give you some examples. And another deficiency could be if you have more anions in the interstitial spaces, which is practically not known because anions going into interstitial spaces is unlikely they being larger in size. So I think, this far and no further, and if you have noted it down, you would not find a question on crystal defect out of reach. When I see you next, like tomorrow, I'll be solving a lot of questions of physical chemistry which I have shared in the group. All the doubts which people have sent me, including the ones which you have sent me, and the questions on solid state. Tomorrow I don't have a class as such, so I'll have more time, and online, I'll be able to cater to more of your questions and doubts. This much for the time being, I believe. Stay happy, stay healthy, time permitting. मैं ना colloids भी पढ़ा दूंगा. It will again take me 40 minutes, 45 minutes to instead of giving you notes, I can actually make you write it in your own handwriting. Half an hour, 40 minutes colloids हो जाएगा, exhaustion हो जाएगा, तो उसका जी एडवांस क्वेश्चन भी देख लेंगे. WBGE में भी ऐसा करके. So this much of the time being, I believe. Thanks for attending the class. Stay happy, stay healthy. See you all. Bye-bye.
Bye.